Hi, I'm Raj Gill.
I'm Sean Perande.
And I'm Tasha Coote.
We are fourth year integrated engineering students at the University of British Columbia. Hello, we are Group 10 and we are the Polycotton Textile Fiber Separation Group. We chose to work on this project because we wanted to decrease the amount of textiles that end up in landfills. As Canadians, the average individual sends about 81 pounds of textile waste to landfills annually, and North Americans are responsible for creating about 9.5 million tons of textile waste every year, most of which can be reused or recycled, which would reduce the amount of virgin material needed to be produced and allow resources to be used for other applications. The fibers have a total of 5 forces acting on them as they travel through the separator. The first is gravitational, the second is drag force caused by air friction, the third is centrifugal force due to the rotation of the drum, the fourth is pinning force caused by the corona electrode, and the fifth is electrostatic attraction or repulsion due to the electrostatic electrode. It was originally assumed that the electrostatic electrode would be positively charged and therefore attract the polyester fibers as they're strongly negative according to the triboelectric series. However, through testing, it was found that the electrode was actually negatively charged and attracted the slightly positive cotton fibers and repelled the strongly negative polyester fibers. And while our original assumption may be wrong, the key principle of separating the fibers by exploiting where they fall on the triboelectric series still held true. The only difference would be which bins the fibers would be collected. Testing done at CMP was to determine the effects that output voltage, material type, and material processing variation would have on fiber separation. The output voltage ranged from 16 to 24 kilovolts. The material tested was cotton and polyester, and the material processing variation determined the type of sample being fed. The two types were a square sample and a fluff sample. Testing was done by hand feeding homogeneous batches of sample onto the drum, allowing them to be collected into the 3 bins below. The bins would then be analyzed to determine how much sample was collected in each, and the data would be recorded, at which the output voltage would be increased by 2 kilovolts until reaching a final output voltage of 24 kilovolts, after which the output voltage would be decreased to 16 kilovolts and a new material type would be used for testing.
This first video shows the behavior of polyester. Notice how it's pinned to the drum and falls into the left-hand side bin. This second video showcases the behavior of cotton. Notice how it is attracted by the electrode on the right-hand side, shot into the air, and pulled over into the right-hand side bin.
Lab testing was overall quite successful. It showed a strong potential for electrostatic separation, with the most successful procedure isolating 90% of the cotton sample. The figure on the left shows the data from that test run, where black and red bars represent the respective portions of polyester and cotton samples that settled into the far right bin. At low voltages, both samples naturally fell into the far right bin together. However, by 20 kilovolts, the pinning force on the polyester was enough to start majorly forcing it into one of the other 2 collection bins. By 22 to 24 kilovolts, the polyester was completely removed from the far right bin, leaving just cotton. However, at voltages over 24 kilovolts, the competing electrode forces became too intense and interfered with the expected particle flow. This successful testing was seen when the fluff particle of 1 cubic millimeter was used, without any previous contamination of the sample. The most successful round of testing, seen again on the top figure, was performed with particles that were processed by hand-cutting strips as small as possible, and then pressing them through a mesh strainer of 1 square millimeter size. However, testing was also conducted with particles processed in different ways, into different geometries. Most notably, particles were cut into strips of a 2.5mm width, and further cut into squares. Testing on these particles was conducted in the hope that simpler sample processing would be sufficient for particle separation. However, as seen on the bottom figure, both the cotton and polyester behave much the same at each voltage, with their proportions in the right bin being nearly identical. This was likely due to a number of factors, such as higher surface area inducing a higher pinning force onto the drum, and existing woven connections keeping the particle from becoming airborne. As a result, the cotton stayed adhered to the drum, mimicking the path of the polyester.
This video showcases the behavior of larger strip cut particles failing to be pinned to the drum.
We also tested the effects of sample reuse on separation efficiency. The faded red bars in the figure on the left represent the successful testing described earlier, showing the proportion of cotton in the right bin. The dark solid bar shows a similar batch that was already used in previous testing. This batch observed more varied results, likely due to contamination or the accumulation of charge. The implication here is the need for a high enough efficiency to begin with, in case separation is less successful afterwards. These tests ultimately show positive signs for electrostatic textile separation. An initial requirement of the project we set was 90% separation efficiency, and we saw that in the testing described. That being said, we were only able to analyze heterogeneous batches of cotton and polyester, so we aren't able to draw too many conclusions regarding true blended textiles. Testing also exposed how critical the process of decomposing the fabric was to the success of testing, showing that smaller, fluffier particles that had more time put into shredding them responded a lot better than strip or square cuts of fabric. Extra constraints like this, as well as the cost of high-voltage power sourcing, implies that smaller operations might be less able to ultimately take on a technology like this. If anything, it seems more probable that larger entities like recycling plants or corporate initiatives might be able to see it through.
Throughout the term, we have created two prototypes, a lo-fi and a hi-fi. The lo-fi was created using a plastic drum covered in aluminum foil and copper wires as the corona electrode. The DC power supply only had a range of 30 to 60 volts, and we wanted to see if we could generate the corona discharge at this lower voltage. As expected, we did not see any response as we were orders of magnitude lower than where we needed to be. Our second prototype, which would be used for Design and Innovation Day, was modeled after the electrostatic separator available to us at the coal and mineral processing labs. The main problem our group ran into was the acquisition of a high voltage power supply, which is necessary to produce the corona discharge. Fortunately, we were able to secure the power supply at the end of February. Unfortunately, the maximum output voltage of the power supply is only 20 kilovolts, and the best separation is found to be at 22 kilovolts. The power supply is also missing its outputs cable, which our group has ordered but will not arrive before Design and Innovation Day. As such, our group decided to shift its focus onto creating a display model for Design and Innovation Day that would be missing the power supply. The metal drum was fabricated by the material shop.
This video showcases the drum rotating successfully within a temporary prototype base. In this design test, we wanted to confirm that the non-circular cross-sectioned shaft would rotate smoothly within a circular hole in the wood. The electrical circuitry for the motor is relatively simple. Drum speed is controlled by the value of the resistor in the circuit. At this point in our design, we would manually swap out resistors to obtain different drum speed values. A design choice was made to separate the motor circuit and the electrical circuit for simplicity and safety reasons. Note the grounding of the drum. The drum must provide a discharge path to ground in order for the electrostatic system to work. Grounding the drum proved a mechanical challenge, with the constant unidirectional rotation prohibiting a simply attached wire and requiring a stationary metal grounding component in constant contact with the drum system. Our group theorized we could use metal bearings to mount the shaft to the wall, connecting the ground wire to a screw in the bearing.
Using a steel blade that is commonly used for X-Acto knives. The steel blade was then fixed to a piece of PVC piping to allow for safe handling. This was done by creating a slit in the PVC pipe and screwing 2 screws into the blade, allowing the blade to be fixed to the pipe while still allowing for small changes in positioning of the electrode itself. Power was supplied by attaching a wire to one of the screws. The electrode was then mounted to the back wall using 2 PVC pipe straps. The electrostatic electrode was made and mounted in a similar manner.
To provide safe insulation from the high voltages, a design choice was made to avoid the use of metallic or other conductive materials in the enclosure design. Wood and acrylic are used with glue joints. To facilitate removal of the sorted bins, an inner platform at the bottom pulls out like a sliding drawer. All components and wiring are mounted to the wood back wall. The joint top and side panel can be removed entirely by lifting up, permitting ease of access to internal components for troubleshooting and design, while avoiding the need for metal hinges. The high voltage power supply unit is not encased within the enclosure and would be connected externally by a well-grounded cable. Due to the current lack of a cable, this design feature will be explored further at a later date. We will now discuss some of the impacts the coronavirus had to the completion of this project. A detailed breakdown of post-corona deliverables versus original design path can be seen here and is explored in further detail in the accompanying report. Access to UBC campus was restricted just prior to our group completing final testing. Recent weeks of testing had primarily used single material samples, attempting to understand the impact of particle size, particle weight, sample preparation method, drum speed, and voltage on sample behavior. Mixed material testing was to restart the following week. Enclosure components had been fabricated, with assembly and attachment of the wiring and electrical components remaining. The mechanical drum system was fully assembled and tested. Unfortunately, our group was unable to gather our things from UBC, thus could not continue building from home. Paper prototyping was done for a hopper and collection bins. The cell phone video and photography collected during the testing was intended only to serve as a reference point, with plans to capture very high-quality video and photography since the beginning of the project design. Unfortunately, we had scheduled to gather our high-quality footage with professional gear on the week following UBC shutdown. Existing image proved too low quality to apply the image processing methods, so image processing was demonstrated on an inaccurate replacement sample. Our team is interested in completing the device when government regulations allow. Tasha and Raj will remain at UBC for an additional year. We are both interested in further pursuing the findings from this project and are pursuing options to continue researching independently. In our original design scope, we aimed to make a tabletop device to target the hobbyist and makerspace market. Due to the high cost of a high voltage power supply, we expect our device will prove more viable for large-scale industrial clients, such as clothing manufacturers or municipal recycling centers. Volume and feed rate capabilities would need to be scaled up, and the device would need to be integrated with industry-standard conveyor systems for both input and output streams. A medium-scale future may exist for this device within the Vancouver film industry. This idea was proposed to our team by Nikita Wiley, a local clearance coordinator and costumer, with interest in aiding the funding and commercialization of the device. Upon wrapping up production on a show, vast warehouses of clothing are disposed of in landfill. The majority of these clothes are unacceptable for the secondhand market due to costume dirt, fake blood, or other film products. Ecological impact and improving recycling processes are high priorities for industry-wide improvement in film.
Thank you for listening. We hope you've enjoyed our presentation.